So this time I'll be talking about debugging neural networks for NLP. So this is something that's relatively important and something I didn't even think about doing until like a week or so ago. But I think this is good to know. I think there will be a lot of questions this time. So if you have questions, feel free to ask as well. So in neural networks, one of the good things about neural networks is they're extremely powerful and they're good at getting good results. One of the bad things about neural networks is everything is a hyperparameter in neural networks. So this means that you need to tune them appropriately to get the absolute best performance. You can do pretty well without tuning, but if you do tuning, you'll get better results usually. So some of the things that are worth tuning are network size and depth. Small variations in the model. Do you use a TANH or do you use a ReLU or do you use something else? How you create your mini batches. What's the size of your mini batches? What order do you create them in? What is your optimizer? What is your learning rate? And et cetera, et cetera. And models are complicated. They're often somewhat opaque, and debugging can be difficult. So the idea is how do we do this in a more effective way? So I think the first step, I talked about this very briefly before in kind of an informal way, but the first step to debugging is understanding your problem, understanding which part of your code the problem is likely to be a result of. And a typical situation is basically you've implemented a nice model that you think should be working. You've looked at the code and it looks okay, but your accuracy on the test set is bad. It's not working at all, or it's not working as well as you would expect it to. So, so what do you do? There's a lot of possible causes for bad accuracy, and one thing that I think is really, really important for effectively debugging is to understand these causes and be able to diagnose these causes. So one of them is training time problems. So basically, you have this model that should be training, but for some reason, it's just not learning to fit the training set well. And if this is the case, this means you either lack model capacity, for some reason, you have an inability to train the model properly. For example, your optimizer is not good, et cetera. Or you have a bug at training time where your model is just not what you expected it to be. You can also have decoding time bugs or basically search bugs that don't allow you to search for the answer properly. This is especially common in structured prediction models where you need to take one prediction and feed it back into your model. And these can often result from a disconnect between between training time and decoding time, not test time and decoding time, training time and decoding time. It can also result from a failure of your search algorithm to find the best result. Another problem that maybe many of you are familiar with now is overfitting, and also a mismatch between the optimized function and what you're finally evaluating your model on. And all of these are different things. They have different symptoms and they have different solutions. And if you just look at this and you train your model and you're getting bad test accuracy, you don't know which one of these it is. So you don't know which part of your model to debug. So I'll explain about all of these in turn. Any questions so far? Okay. Okay. So let's first talk about debugging at training time. So in order to identify training time problems, how do we tell that our model is not training properly? Basically, the way you can look at this is you can look at the loss function calculated on the training set. Is the loss function going down? So, do you have a nice curve for your loss function that looks like this? Also, is it going down basically to 0 if you let training go along long enough? So, it should, on your training set, it should go, it won't ever reach 0 exactly in most cases. Theoretically, it could reach 0, but in most cases it won't. But it should be going down very, very close to 0 after 20 to 30 epochs. Yeah.
Number of epochs, like, on the data size?
Yeah, it definitely depends on the data size. It doesn't depend on the data size as much as you would think, though. If you have big data, it needs to learn a lot more to reduce the training loss to 0 in order to memorize things. So actually, you'd be surprised by how constant the number of epochs is, regardless of your training size. But if you have more training data, it will need maybe slightly fewer epochs, I guess. 20 to 30 is usually, well, if you're using regular SGD, 20 to 30 is pretty reasonable. If you're using a different optimizer, like more sophisticated optimizer, 20 to 30 is usually more than you need. But I can talk about that later. So if not, you have a training problem. So if for some reason your model is doing something like this, it's not getting close to 0, then you're probably not training. Your model is not training very well. Or if your model is going like this on the training set, then this is also a bad thing, and you have a problem somewhere. Yeah.
Can dropout affect the shape of this?
Dropout will affect the shape. It will definitely make training slower. It will almost always make training slower. It might make it look something a little bit like this. It might not converge completely ever. So if you're adding strong regularization, of course, you might not be able to fit the training data. So if you don't have dropout and you don't have any source of regularization, it should converge to 0, but otherwise it should be like this. It might be like that. Even if you have dropout, it will usually converge to somewhere pretty close to 0, though, I think. So the first problem is your model could potentially just be too weak to fit the training set properly. This is not necessarily a problem. You might want to make your model a little bit weaker so it doesn't overfit as heavily, but in most cases, neural network models do best when they have enough parameters to fit the data. And then you want to add something like dropout to prevent it from overfitting. So it needs to be big enough to learn. Model size completely depends on the task, but some general rules of thumb that I have are, if you're doing something like language modeling, you usually want about 512 nodes. You can get away with 256 or something like this. If you're doing something like natural language analysis, as few as 128 might be reasonable, but bigger can often work better. So if you're using 32 nodes in your recurrent neural network, that's probably not enough, and you're not going to be able to fit the data. Even if you're worried about overfitting, bigger can still sometimes be better. So you'd be surprised by how big you can make your network and still have it learn well without overfitting. Also, multiple layers are often better. So if you want to learn something that's relatively complicated, having multiple layers in your net can be a good idea. This is not always necessarily the case that this will give you big gains, but usually at least 2 layers for NLP related tasks seems to work pretty well. It's especially important to have lots of layers if you expect something to be complicated. So something like language modeling, for example, predicting the next word requires you to kind of, push things on a stack, pop things off the stack, kind of remember your state with regards to several previous words and combine them together in complicated ways. And because of this, having multiple layers allows you to create more complicated functions in a smaller number of parameters. So this can help. really strong machine translation models, for example, tend to have 6 or 8 layers. You can do pretty well with only 1 or 2, but if you want to get the absolute best accuracy, adding many more can help. Also, for very long sequences, if you're using recurrent neural networks, you often need larger hidden node sizes. You need larger sizes in your RNN. So for example, if you want to build a word-based language model, 256 or 512 might be enough. If you want to build a character-based language model, you'll want something like 1024 or something bigger. Anybody know why? Any ideas?
Remember the long-term memory?
Yeah, basically you need to remember, so you need more memory capacity. Another way to interpret it is you need to remember not only what word you're in, you need to remember what position in what word you're in. So you need to be more fine-grained about what position you're in, and having a larger network can help you with that. So in general, this is another important thing to remember.
How long do we need here for the long sequences? How many words?
Well, so for example, if you're doing character-based language modeling, that will be 5 times longer than your number of words. So instead of having 40 words, you'll have 200 characters. For something like speech, you might have 1,000 frames, 1,000 speech frames. Okay, anything? Yeah.
So if the model fits the training data perfectly, does it mean that we have enough nodes for it?
Oh, that's an excellent question. So if the model fits the training data perfectly, does that mean we have enough nodes? No, it doesn't. And the reason why is because it might fit the training data in a very strange way. It might fit it in a very, in a way that's not actually generalizing appropriately. And it's very hard to tell whether that's the case or not. But I guess one symptom is if it's taking a long time to converge with few nodes, and you increase the number of nodes and it's suddenly converging much faster, then that's probably a sign that you want more, nodes. If you increase the number of nodes and it converges at about the same speed, then that might, then you might not need as many nodes. But that's just a complete rule of thumb. That's something that I've noticed, and I don't have any theoretical grounding behind that. Yeah.
And with regard to your longer sequences, like
Yeah.
like few thousand, like 2,000, and it seems usually memories are usually very difficult because
Yeah.
Do you have some suggestions for that?
Yeah, it depends on your task. If you're doing something like language modeling, there's something called truncated backpropagation through time, where you only calculate a piece of the sequence and backprop through the piece of the sequence. If not, reduce your mini batch size. Use something other than an LSTM that's a little bit more memory efficient. Like CNNs tend to be more memory efficient than LSTMs do. But yeah, I guess those are the major things. Oh, use multiple GPUs. If you have a multi-GPU machine, you can put part of your model on one GPU and another part on another GPU. So I guess those are the main things. Okay. Oh, one other piece of advice is if you have variably length sequences and you're creating mini batches, if you create mini batches by the number of sentences, your maximal memory consumption will be maximal mini batch size in the corpus times number of sentences. So if you have one sentence that's 1,000 words, and most of the other sentences are 100 words, then you're going to be wasting a lot of memory capacity. So what you can do instead is you can create mini batches by the number of words in the mini batch as opposed to the number of sentences in the mini batch. This is something that not a whole lot of people do, but I really like, and it seems to work well for me. But you could try that. Okay. So one thing is just because you increase your memory capacity doesn't necessarily mean it's a good idea. So if you have deep models, extra layers can help, but they also have the potential to make learning much, much harder. And this is simply because of the vanishing gradient problem, where if you have a model that's 8 layers deep, you might not be able to learn the earlier layers of the model because the gradients propagate back and they disappear while they're propagating. Fortunately, now there's a bunch of solutions to this that work pretty well. So residual connections. So the idea behind a residual connection is basically you have a weight layer, then something like a recurrent, a rectified linear unit, then another weight layer. But then you add the previous input here. And by doing this, basically what you're doing is you're passing the previous vector as is all the way from the beginning of the network to the end of the network. So this identity function will not result in the gradients disappearing. So if you do this, basically you're guaranteed that you won't be hurting your accuracy by adding more layers, because it can learn to just ignore the earlier layers and rely entirely on this identity function. There's also highway networks, which are very similar. They were proposed at a very similar time, but this is one where you basically have a gating function. So this T here is a gating function that decides whether to use the transformed input or the identity input. And both of these have been used successfully in NLP tasks. Okay, so next is trouble with optimization. So if increasing model size doesn't help and you're still getting something like this, you might have an optimization problem. So possible causes for this include a bad optimizer, a bad learning rate, bad initialization, or a bad mini-batching strategy. Mostly the first three, also partially the last one, but it's generally one of the top three. So if you remember, I talked about this at the very beginning of class, so probably everybody's forgotten it by now, but there's a bunch of optimizers. You have things like SGD, which simply takes a step in the direction of the gradient. SGD with momentum, this remembers the gradients from the past time steps. Addigrad, adapt the learning rate to reduce the learning rate for frequently updated parameters. Atom, like Addigrad, that keeps the running average of the momentum and gradient variance, et cetera, and many others. If you just want to optimize the training loss, Atom seems to work quite well. Atom is stable, it tends to work and get you to a good optimized place most of the time. So if you're encountering something like this and you're not using Atom, I would suggest trying it out. But I'll talk about some reasons not to use Atom later in the slides. Okay, so learning rate. Learning rate, it's an important parameter of your model. If it's too low, your model will not learn or will learn very, very slowly. If it's too high, it will learn for a while, then fluctuate and diverge, or never, converge to a good point. So a common strategy is to start from an initial learning rate, then gradually decrease your learning rate as training goes on. So one way you can do this is you can train for like 5 or 10 epochs and then just arbitrarily have the learning rate every epoch. If you have big data, this is a pretty common and effective strategy. You can also use a development set, which I'll talk about in a little bit. Another very, very important note that people might not realize if you're not familiar with this is different optimizers require different initial learning rates. So SGD's magic initial learning rate is 0.1. It works a lot of the time. Atom's magic initial learning rate is 0.001. This works a lot of the time. But these are things that can be adjusted. So it's very common for SGD to range between 0.5 and 0.01. So maybe 5 times this to 10 times smaller than this, it's very common for atom to be a bit smaller than this. So 0.001 to 0.0001, like up to 10 times smaller. So when you're reading a paper, don't ignore this. This will only be one sentence in the paper, but if you read it, if you read that sentence carefully, this might be something that will affect your results. Especially if it's something other than the default. If they set it to something other than the default, then there's a pretty good chance that they tried the other ones and they had an effect. Any questions about that?
Do you have a comment on the relationship between learning rate and batch size?
The learning rate and batch size. This is a really difficult question. And the reason why it's a difficult question is because there's 3 factors here. Actually, I forgot one other thing that's important, and I didn't put it on the slides, but there's also something called gradient clipping. So gradient clipping is a thing where basically you take the gradients of all of your parameters and you calculate the norm of the gradients. So let's say these are the gradients of all your parameters. You calculate the norm of the gradient and then divide your gradients by this and multiply it by some constant c. And for example, a lot of the time the c is 5, which is arbitrary. In Dynet it defaults to 5, in other toolkits it defaults, I think, to 5 a lot of the time. But this is really important because if your gradients fluctuate in scale a whole lot, it makes training unstable. So this is like a common thing in neural network toolkits. Now batch size. If you make your batch size bigger, for SGD at least, that will make your effective learning rate bigger. But if you're doing gradient clipping, it will actually not make your effective gradient bigger because your gradients will be clipped anyway and they'll all end up being this. Also, some toolkits by default average your gradients when you do things over batches. So if you average the gradients, then that will also make things similar. So that's a good question, but there's no super clear answer here. Okay, anything else? Okay. Initialization. This is something that you don't need to think about quite as much, but it can still make a difference in your results. So neural networks are very sensitive to your initialization because this results in different sized gradients for the models. There are a lot of different standard initialization methods. One is Gaussian initialization, where you initialize with a zero mean Gaussian distribution. Another one is uniform range, where you just pick a range uniformly, maybe between minus 0.1 and 0.1, and then you initialize everything to be uniform with that in that range. There's also more intelligent initialization strategies that basically initialize in a uniform manner, but where the range is specified according to the net size. In the default depends. In Dynet, the default is Glorat initialization, and then there's also, in other toolkits, it might be different. This is just to give a very, very simple intuition. If you have something like a matrix W, and you have a hidden state here, the idea is when you multiply this by the hidden state, you should be getting something that is in a reasonable range, close to 0, and not changing the variance of this very much. So if you make it, for example, much bigger than what you get from here, you're going to get things that explode or get much smaller when you do this matrix multiply. Okay, so next, sorry, there's lots of things here, so I'm going relatively quickly. I'm happy to take questions about any of them. So the next one is about how you do mini batching. So if you remember mini batching in RNNs, we take multiple sentences. We do padding. We calculate the loss according to each of these. We do some masking to remove any extraneous losses. Then we take the sum. And this, I think a lot of people have realized, speeds up your training immensely, especially when you're training on GPUs. In order to do this, you basically need to get sentences and put them together in a single mini batch. In order to do this, it's much better if you do it sentences of similar length. So if you do sentences of vastly different length, you'll have lots and lots of padding and masking, and that wastes your computation time, basically. So one way to get around this is bucketing or sorting your sentences. So if we use sentences with different lengths, too much padding and sorting can result in the training being slowed down. So to remedy this, it's very common to sort sentences so similarly length sentences are in the same mini batch. And I think the coding examples that we have shows this. And what this means is basically we have sentences of length 15, 14, 14, 13, 12, 12, 12. And we sort to make sure they're in this order, and then we divide into mini batches of size 3 and then process these all at the same time. Maybe it's size 3 or size 32 or something like that. So this is pretty common. One thing to be aware of is that this is not necessarily benign. It can affect your performance. So we have a paper where we did this not only for single sentences, but we did it for machine translation, where you have source sentences and target sentences. And based on how you sort your source sentences and target sentences, you get different results. So it was worse to sort by the target sentences than it was to sort by the source sentences. And the most stable thing was just to randomly shuffle the sentences. So don't do any sorting at all. And kind of randomly shuffling makes sense from a machine learning point of view. You don't want to have bias in each of your mini batches that cause you to jump in one direction or another direction. But this was a kind of interesting finding that made me realize that this is relatively important. Okay, so this is training related stuff. Are there any questions about that or anything that I missed? That people noticed? Yeah.
Default initialization method in dynamic parameters.
Oh, it's Glorat, which is what I had up there. Anything else? Yeah.
So that normalization is supposed to help with the divides in the sort. So is that the analysis based on?
Yeah, so batch normalization is not, it's kind of something that's a little bit different than what I was talking about here. So batch normalization, just to give a very brief summary, is you look at all the elements in your batch and you normalize each node or each value basically with respect to the other elements in the batch, so that things become, I believe, zero mean and unit variance, plus multiplied by a constant and adding a bias or something like that. And the motivation behind this is classifiers in general and neural networks in particular like things that are normalized, so that they aren't. They don't like values that are like 500, 499, 500, 501. Stuff like this. The reason why this is bad is if you multiply this by a weight and then use that in your activation in your next layer, you're going to get things that have this huge scale. And then if you have a tan H, for example, things will be saturated to the very edges of this tan H, and you don't get any gradient. And that's part of the reason why initialization is so important, The idea behind batch normalization is that if like the outputs of your network are getting these really huge values or values that aren't centered around 0, you would like them to be close to 0. So, for example, you might take the mean. And subtract the mean, which would give you 0, -1, 0, 1, which is much easier for nuts to handle. This is a trick that's used to make training easier, and it's something that people could consider using, but it's not directly related to this. Although maybe if you made your batches larger, then batch normalization would work better, but I can't say much more than that. Does that answer the question? Okay.
With regard to when you have word embedding and for to the RNN, how do you do the batch normalization? Do you like normalize over embedding or?
You could normalize over embedding space. Word embeddings are actually relatively easy because they're fixed inputs. So if you wanted, let's say you had pre-trained word embeddings, if you wanted, you could just normalize all the word embeddings to be like 0 mean and unit variance before you even started using them. That would probably work as well as batch normalization. If they're not pre-trained, then you might want to normalize their norm to be a fixed size. There was actually a paper that just came out that was very effective at machine translation that fixed the norm of your word embeddings. But if it's an input, you can do feature whitening before you even start using your neural networks. Okay. So I will move on to debugging stuff. So all the stuff that I did up until now is kind of figuring out how why your neural network isn't converging properly. These bugs or these problems are not necessarily the easiest to track down, but they're not impossible to solve. Like you can, if you have kind of the tricks that I mentioned here, you can kind of figure out ways to make your net converge more stably. Debugging at decoding time. This is really annoying, but it's easy to do. And if you just spend enough time on it, you can find your problems here. But it's also a really big problem for any kind of structured prediction you're doing. So the reason why you have a problem at decoding time is basically because you're training your model to do something different than you're asking your model to do during inference. So the reason why this happens is usually because your loss calculation, which you use at training, in your decoding will be implemented in different functions. So for example, in our example of encoder-decoder.py, we have a loss function that calculates the loss, and we have a generate function that actually generates the output. And if you're aware of kind of the principles of software engineering, in software engineering, the absolute worst thing to do is, maybe not absolute worst, but one of the worst things to do is to copy and paste code. Copying and pasting is the best way to introduce bugs into your system. So basically what we're trying to do, what we're doing with calc loss and generate is we're copying and pasting code. We're copying our calc loss code into our generation code. And any place where we're doing the same thing in different functions is a potential cause of error. Another thing that makes things harder is usually loss calculation is done on the mini batch level. So you have mini batch calculation for your loss, which makes things more efficient, but your generation is not. I'm talking exclusively about structured prediction problems here because many of the things we do in NLP are structured prediction. But if it's not structured prediction, the situation's a little bit better, but you can still make mistakes. So first, debugging mini batching. So how to debug mini batching is pretty straightforward. You calculate a loss with a large batch size. You calculate the loss for each sentence individually and then sum those 32 losses together. And the value should be exactly the same modulo numerical precision errors. So probably about 10 to the minus 5 The difference should be 10 to the minus, no more than 10 to the minus 5. Usually it's like 10 to the minus 8 or something like that after dividing by one of the values. And I highly suggest, if you have unit tests in your code, to create a unit test that tests this for you for the common models that you're using. And this will be very good at kind of figuring out errors. So just to give you an idea of where these errors can occur, as I mentioned before, when you do mini batching, if you're doing this kind of padding and masking, if you do padding and masking wrong, it's likely that your mini batched function will diverge from your non-mini batched function. And that's a very good way to kind of catch this problem and realize that you have something different. In reality, sorry, let me go back here. In reality, this is the smallest problem that you can have I think this is generally the smallest problem that you can have regarding decoding. The difference between mini-batched calculation and batch calculation, especially if you're doing something like sorting by your source sentence. For a while, my machine translation code didn't even do padding and masking at all, and it worked pretty well. But if you do padding and masking, it does help you a little bit, especially when your data is very small. So this is one way to test whether it's working well. So the next thing, this is super important. This can totally destroy your results if it's not working properly. So debugging decoding. So your decoding code or your search code, basically the scores that you calculate in your search code should get the same loss, or should get the same score as your loss calculation. So what you do is you calculate the loss. You use your calc loss function to calculate the loss of a correct answer. And then you perform forced decoding. So basically the idea behind forced decoding is if you're true, or this is an example. If your true output is this is an example, you call your decoding function, but you also pass in this output. And everything in your decoding function is normal, but you have one switch that is if forced decoding, select reference, else select model artifacts. So the idea is if you pass in a reference, you generate the word from the reference. If you don't have a reference, you just select the artifacts that your model likes. And then if you do this, you can basically force your model to generate the reference sentence or tree or whatever you're trying to generate. And then you keep track of the score. And the score that you get when you do forced decoding should be exactly the same as the score from your calculate loss function. If it's not exactly the same, this means that during training time and during test time, you're calculating different functions. And this is a big problem. This will cause you anything from small errors to just completely not getting any output at all. And yeah, the score of the two should be the same, and you can also create a unit test for this. So this will help prevent regressions. And you can have a whole suite of unit tests that for all of the models you're interested in basically tests all of these things and makes sure that there's no problems. Okay, any questions about this? No? Okay. So next is beam search. Dan is going to talk about beam search on Thursday, so I won't talk about it in detail, but I think a lot of people know the general idea, which is instead of picking the single highest probability path in greedy search, you pick, you maintain multiple hypotheses at any time step. So you might maintain 2 hypotheses at any time step. And by doing so, you tend to get better results. So this will be more on Thursday, but this is also a place where you can make mistakes if you implement search incorrectly. So basically, as you make search better, the model score should get better almost all of the time. It's actually not guaranteed that you'll get a better model score by doing beam search, but almost all of the time you'll get a better model score, and especially you will if you look at your entire test corpus. So you run search with varying beam sizes and just make sure you get a better overall score with a larger beam. And also create a unit test for this. So this is how to debug problems in decoding. Any questions? Another thing that is very helpful for a number of reasons is to look at your data. I highly recommend looking at your data at model design time. In fact, in the assignments, we kind of enforce this in a way by grading analysis of the data. But also, when you're debugging problems, it can be useful. It's often not super useful. But sometimes you can just look at the outputs and realize something is obviously wrong. So this is one example that I've seen before. The model is just deleting the first word of your output every single time. It was an off by one error where we intended to delete the start of sentence symbol, but the start of sentence symbol wasn't appended to our sentence. So we got a blue score for this. We got a blue score for this that looked pretty okay. It was like 17, but when we fixed this bug, it went up to 21. So that's a big improvement. So this is my favorite one. So our system was making University of Nebraska at Kearney an unknown word. So the abbreviation for University of Nebraska at Kearney is UNK. So I don't actually know exactly how the person who found this, but I think our vocabularies didn't match or something like this. But if you look at your data, sometimes you can realize these strange errors as well. Okay, so this is the problems of training time and decoding time, or training time and inference time mismatches. The next thing is battling overfitting. So this is much harder than any of the other things because there's no correct way to do this. But it's very important to know when everything is working properly, but you're just overfitting. So basically training loss converges well, but test loss diverges. I think most people here know the symptom of overfitting, and it looks something like this. So you see our training loss goes down relatively quickly, and it's continuing to decrease. But the test loss goes down for a while, and then it starts getting worse and worse. So this is symptomatic of overfitting. One thing I should mention here is that if you're worried about overfitting, you don't even need to look at your accuracy. Your accuracy is going to fool you. Because your accuracy and your loss are not the same thing. So you're optimizing your model to improve your loss. So you should be measuring your loss on your development set. And if your loss looks like this, then you're overfitting. If you just look at this simple example was done on MNIST, I believe, which is a simple image classification thing. You can see the loss starts getting worse very quickly, while the accuracy does not start getting worse. So it's not necessarily the case that looking at the accuracy will let you see that you're overfitting. So the first important thing to know is that in many cases, barring the cases that I talked about training, your neural network can memorize your training data. So this was a paper that was kind of interesting and widely cited. But basically, if your neural network has more parameters than training example, or your neural network will almost always have more parameters than the number of training examples that you have. And what this paper said is basically if you randomly shuffle the training labels, in other words, there's no correlation between input and labels. The only way it can get good accuracy is by memorizing each individual example. You can see it can still learn to get a reasonable loss function on the training with random labels. So the blue one is the true labels. This is where it's actually learning the true function that you want to be doing. And you can see it's much, much easier to learn with true labels. Like, that makes sense, right? You know, it's, it should be easier to learn with true labels. But even with the red, like, worst case scenario where you randomly shuffle the labels, it's still able to reduce the loss after an epoch or two. Or actually, importantly, it's still able to reduce the loss after the first epoch. Because the first epoch, it's just seeing random labels, so it can't reduce the loss at all. But after that, it's able to reduce the loss. And they also did things where you corrupt the labels, etc. So given this, because your neural network can memorize your training data, the only thing that it's quite possible that it will learn to memorize the training data, but not learn anything useful to generalize to the test data. And if that's the case, we need to know why, and we need to know how to fix this. The best way to prevent overfitting is to make a better model, is to make a model that's really, really easy to learn. And if you make a model that's really, really easy to learn, then it won't overfit. It will learn well. So one reason why overfitting occurs is because you haven't done a good enough job and you need to do better. But even if that's the case, even if you have a pretty well thought out model that works well, there's also a lot of things that can cause overfitting to happen anyway. So the first kind of rule of thumb that I think a lot of people knew for a long time, but nobody actually wrote a paper about until like a few months ago, was that adaptive gradient methods like Adam, they tend to overfit more than stochastic gradient descent. So adaptive gradient methods like Adam are very, very fast to learn. They will very quickly optimize your training data or your training loss, but they tend to overfit a little bit more. So a training curve that you often see, is something like you have SGD going down like this, and then you have Adam going down like this. But it kind of levels off, or maybe even goes down like this and then kind of takes off later on your dev set. Of course, on the training set, it goes down to a good place, but on the dev set, it will overfit more than SGD tends to. So this paper examines that a little bit, but I think this is something that, you know, if you've tried different optimizers, you'll have realized. So as a reminder, I also talked about this at the beginning of the class, but we have early stopping and we have learning rate decay. So we want to prevent them from overfitting. And one way we can do this is by monitoring our performance on a held out development set. So we hold out our development set, and the moment we start getting, or we remember the model that did the best on the development set, and then we use that to test our models. So once it, in the case over here, we would be, you know, taking the model from this point where we got the best development set class. It also sometimes or very often helps to reduce the learning rate and continue training. So reducing the learning rate and continuing training, if you have a lower learning rate, it becomes harder to overfit particular examples. So this is pretty effective. So development driven learning rate decay. So you start, sorry, this repeated, but you start with a high learning rate, then degrade it when you start overfitting the development set. So this is kind of like, it's similar to early stopping, but instead you're lowering the learning rate. This is apparently called the newbob learning rate schedule. I don't know who Bob is, but it was probably somebody, I think it was probably someone in speech recognition, because I see the speech recognition people saying this, but it's apparently called the newbob learning rate schedule. In experiments that we did Atom with learning rate decay, and this ended up working pretty well for MT. We were actually surprised by how much better it did than SGD with learning rate decay. One crucial difference between what we did and I believe what this paper did is here they also did learning rate decay for Atom, but we re-initialized the Atom parameters, the momentum parameters, to be 0. And I think that kind of jolts Atom out of a local minimum that it's approached. But I think kind of people are coming up with strategies for doing adaptive learning properly, and I think you'll probably see more papers talking about how to do this well. Yeah.
So adaptive learners, learners that keep on the average are supposed to reduce variance.
Yes.
So how is that consistent with the system adaptive report?
So adaptive, I think basically the basic intuition between adaptive, behind adaptive learning rates mathematically might be to reduce variance, but you can actually think of it more, especially in NLP, you have a lot of sparse parameters in, for example, your word embeddings. And a word embedding for a particular word doesn't get updated unless you see that word. And because of that, basically your rare words are going to get many fewer updates than your common words. And adaptive learning rates, basically, mostly what they do is they reduce the learning rate every time they do an update. It's not completely that clear, but every time you update the parameters, basically you reduce the learning rate a little bit. And maybe it recovers after a while or something. So the intuition behind why Atom works a lot better is because it does big, bold learning rate updates for rare parameters, and it does small parameter updates for common parameters. So your dense parameters in the net that you use for every example get updated in a small step, but the rare ones get updated in a big step. And I think why would that cause more overfitting? You could also argue that it's probably updating those rare parameters too much, and it would be better to be more conservative in how you do updates at the beginning until you actually know what part of the space you should be in. But I honestly don't have a very clean and crisp explanation for why they overfit.
I think there's also the momentum term. Like you have the adaptive learning rate, like in undergrad, and then it might decay too fast. So we might end up not going far enough.
So the comment was that there's a momentum term. So in Adagrad in particular, you always reduce the learning rate.
So undergrad is like without momentum, so the problem is just decaying the learning rate too much. And then in like Adam, you also have the momentum. So they are like two different terms compared to SGD with probably different impacts.
But Adam also takes the running average, so it can recover. So its learning rate can recover after the learning rate has dropped. Adagrad, the learning rate just drops, and that's obviously a bad idea. It will, stop learning after a while. So yeah, there's also a kind of momentum term that keeps a rolling average. I'd like to think about this more and come up with a better answer, but the basic intuition is that they update the rare parameters more than others. So one other thing, dropout is usually a good idea to use. So dropout means you randomly zero out nodes in the hidden layer with probability p. I talked about this before. I guess the only real thing about dropout is it does make things, it makes training take longer. It makes things a little bit more less stable, and you tend to need a bigger network if you're using dropout. If you're, it's not quite as clear cut as this, but if you have a network of size 256 and you do dropout with a probability of 50%, it's a pretty good idea to make your net twice as big and make it be 512. Yeah, and then scaling is necessary, but I talked about this before.
What about input dropout?
Oh,
This is layer dropout, right?
this is layer dropout. You can also drop out whole words in the input. That's another thing that is useful. Is that what you meant by input dropout?
Yes.
Yeah, so you can drop out whole words in the input. That's particularly effective in the output side of sequence-to-sequence models, I think. But you can also do it for things like text classification or whatever. Yeah. I'm not sure. So for text classification, I'm not sure it's a super good idea all the time. Because if you drop out the most important word that is the key to text classification, then you're asking your model to learn from all the other stuff. And that seems like it could also potentially increase overfitting, right? Because you need to remember your examples. So on the output side of sequence-to-sequence models, you already have all the information you need, but on the input side, it's not entirely clear to me. Although I don't think anybody's examined that before. So recurrent dropout, basically we would like to also apply dropout to recurrent neural networks. This is called variational recurrent neural networks because you can also kind of interpret this from a Bayesian interpretation. But the basic idea is that when you apply dropout to a recurrent neural network, you basically sample a single dropout mask for all your time steps. And the important thing is that you're dropping out the same nodes at every time step. If we thought about an alternative where we dropped out different nodes at every time step, basically each time we would lose some of our memory that we need to be using to remember the whole sentence. So the original kind of paper on dropout for recurrent neural networks, or there were a couple papers that proposed the same idea, was that you just didn't do dropout on the recurrent nodes, but by sampling a single mask, you can do this. And this is implemented in most of your neural network toolkits, like Dynet, PyTorch, etc. Okay. Yeah.
So I have a couple of questions about the development set.
Uh-huh.
So one problem is the development set does not represent a set, especially for small data set.
Uh-huh.
So the validation loss fluctuates, so we cannot really use early stuff because we don't know when the validation loss will drop again. And also that doesn't mean that the test loss drops too.
Okay. So you have two problems, which are different problems. So the fluctuating development loss problem, one way to handle this is by adding something called patience, which patience is basically you wait a certain number of development evaluations before you reduce the learning rate. So you might evaluate 10 times, and then you only reduce the learning rate after you've not gotten any better for 10 times. And that is pretty effective at solving the fluctuation problem. The dev and test mismatch, I'm sorry. I wish you had a matched development set and test set, but if you don't, you're not allowed to look at your test set to do anything. So you're out of luck, I think.
Is there any common rule for how to divide testing data into testing?
So that's a good question. How do you divide training, dev, and test data? If you're making your own data set, the best from a theoretical machine learning perspective is to randomly sample instances. So if you can assume that your instances are independent and identically distributed, that makes everything nice from a machine learning perspective. And the way to do that is to randomly sample your dev and test sets. In reality, that might not be a good idea because if you actually want to build a system, maybe your training data doesn't actually match your development and test data, in which case you probably would like to choose your development and test data in a way that matches what you actually want to do. So if you wanted to translate medical documents, you would select dev and test that look like medical documents. So does that answer the question? Or?
Yeah, but is there any like ratio that we should follow? 70%.
So that's a good question. This is about experimental design in general for like NLP or any machine learning. But the size of your development and test set should be large enough that you can calculate statistical significance in your results and have that statistical significance be reliable. So if you, I actually didn't talk about statistical significance testing. I hope you got that in intermediate statistics or language and statistics or all of the other nice classes here. But if you didn't, feel free to ask me questions. But the if you can reliably calculate statistical significance, your dev and test sets are large enough. If not, then you probably need bigger ones. They don't need to be any bigger than that. So if you have 1,000, for translation, maybe you need 1,000 sentences. For classification, maybe you need more. If your accuracy is very high, you might need more. Yeah. Okay. So let me talk about a final one. This is one that people might not think about quite enough, but is actually very, very important, which is a mismatch between your loss function and the final thing that you're writing in your paper. So if you're doing parsing, you might be optimizing the negative log likelihood of all of the parsing decisions, but you're actually measuring your F measure on your parsing of your parser. If you're doing translation, you're maximizing your likelihood and you're measuring your BLEU score. So, but even though the likelihood is getting better, your accuracy might be getting worse or vice versa. And if you remember from our structured prediction talk, we talked about teacher forcing, and basically you're assuming that all your previous decisions were correct when you're doing training and you're not doing it at test time. And obviously that's not a good idea. And that's one obvious reason why your training objective and your test objective could be different. So here's a very, very interesting example. This is not exactly about this is not about the training objective and the test objective, but this is something about where model score is clearly doesn't match your evaluation objectives. So there's this kind of famous thing in machine translation where you have your model score, and if you look at the dark green line, as you do beam search, your score gets a little bit better, then it gets much, much, much worse. And your BLEU score drops off very quickly as you increase your beam size. So you're getting better at searching, right? So you should be getting better. So you are getting better model score, basically. But suddenly your BLEU score is going very far down. And the reason why this is the case is basically because you're optimizing your, when you optimize your likelihood, you get you're basically trying to increase this value when you're doing optimization, but the problem is this value is a whole bunch of multiplications, and every time you multiply a probability, it's getting lower and lower. Your probability gets lower and lower and lower. And basically the beam search is getting better at finding these kind of shorter hypotheses, and the length of your sentences is dropping down a whole lot. And the reason why this happens is basically because you're optimizing this maximum likelihood objective, and you have no way of knowing that, or the model has no way of basically saying, no, it's a bad idea to generate really short hypotheses, which is what BLUE score wants you to do. So BLUE likes correct length sentences. There's a bunch of other examples of this. I'll show one better example again in the next bit. The most principal way to prevent this problem from happening is to actually train your model to optimize what you care about. So if you care about BLUE score, you should be training your model to optimize this. We've talked about a whole bunch of techniques that are ways to do this. So structured max margin training, minimum risk training, reinforcement learning, things like reinforce, reward augmented maximum likelihood. So these are all ways to move your training objective to consider something like BLUE score, or parsing F1 accuracy, or whatever else you care about. Another simple method that, like, one thing I understand is that many of these are kind of difficult to implement. They're much harder, and harder and less efficient than maximum likelihood, except maybe the last one. So even this simple method is one way to help a lot. So if you remember this graph, you can see that basically the loss function on the dev set is getting worse much faster than the accuracy is getting worse. And this is actually a really common problem. So the reason why this happens, I believe, I'm pretty sure this is the problem, is basically your model is becoming more confident at predicting things. And as it becomes more confident at predicting things, it's also confidently predicting wrong things. So confidently predicting a wrong thing is really bad for your perplexity or negative log likelihood. But that's really bad for your log likelihood, but you only get a penalty of one word being wrong if you measure something like BLUE score or something like that. On the contrary, accuracy continues to get better as you start memorizing kind of the long tail phenomena that you're interested in modeling. So the accuracy continues to go up. And this is something I've seen in all kinds of models. It's almost always the case that perplexity starts getting worse before accuracy does. So one simple way to kind of fix this is, instead, when you're doing early stopping or learning rate decay, do it based on the thing that you actually care about, which is something like BLUE score, instead of doing it based on perplexity or your loss function. So this is kind of an extremely rough approximation to any of the nice models here, but it's an approximation that's really easy to implement, and it's something that I can recommend doing. There's one kind of caveat about this, which is you mentioned fluctuating evaluation scores, and accuracies tend to fluctuate more than loss, so you need to add like a larger patience or something like that when you use this method.
I wonder,
Yeah.
What's the patient you usually cite for like the Morishita station?
Mm-hmm.
I mean the number of patients. How do you cite it? 3 times 3 or 5?
The number of what? I'm sorry.
Patients.
Patients. Oh, it's a hyperparameter, but 5 is reasonable. It depends on how frequently you run your
Also
evaluation.
there's a follow-up question. Yeah, how often do you conduct the validation?
As often as you want. Like, one kind of rule of thumb is you might want to spend 5% of your time on evaluating the development set. So, you spend 5% of your time on evaluating development and 95% of your time on training or something like that. So I think it's basically how much time do you want to spend evaluating the dev set. One thing I definitely recommend is don't wait till the end of the epoch. There's no need to wait for the end of the epoch. You should, unless you have very small training data, you might as well evaluate more frequently. So, Yeah, any other questions about this kind of stuff? No? Okay. So I have some final words. The final words are about reproducing previous work, so this is relevant to the assignment and might be useful. Reproducing previous work is hard for the same reason tuning neural networks is hard, because everything's a parameter. Basically, there's no good way to do this other than looking at the code that people have released, if possible, and reducing the differences one by one. So I have a story about something that I did very recently, which is, or I have two stories about this. One, I did very recently. I reduced all the differences in the model, and I got exactly the same model. And then I realized the only difference between the two things that we were doing is how we created mini batches. So how you create mini batches might cause a big difference in your model size. And if you have the code, you can kind of work through things one by one. Another worse thing was when I tried to debug things across two toolkits, and I had to write my own random number generator to make sure that the parameters were exactly the same, and got exactly the same thing tracking the entire training thing until I found this really bad bug that was causing the optimizer to not work properly. So this can be tough, but if you have code that you can use as an example, it's a lot easier. If the code is not released, all you can do is try your best. There's really no guarantee that people will write everything in the papers. So if people are nice, they will. If people are not necessarily mean, but just less careful about writing their paper, there might be stuff that's not in there. But fortunately, most papers recently, the code is released, and even papers from companies recently, the code is being released more and more, which is a very, as graduate students, consider yourselves lucky. This was not the case 5 years ago or whatever when I was a graduate student. So, also, a lot of people don't realize this, but very often if you contact the authors, they'll respond to you very, and be very, very happy to help you. If you think about what it would feel like if somebody contacted you about your work, I think it would feel very good, right? Somebody is interested in my work and cares enough about it to re-implement it. And you would probably want to help them with that. And it's the same for most other people. Of course, it's not always the case. If it's somebody who's very busy or somebody who works at a company that can't release their code, sometimes they won't help. But my experience is 90% of the time that people will be very happy to help out. So, yep, that's all I have. So, any questions or? Yeah.
A question about the beam search. So when you have the beam search for translation, and some sequence can terminate before you reach the maximum number of steps. So how is that usually done?
That's a good question. I'll let Dan answer that next time. Did you hear the question? But you can ask him. Anything else?
Like in beam search, when you do beam search on translation, and some sequence can terminate before reaching the maximum steps, and how you that is always.
Yeah. Well, yeah. Okay. Cool. Yeah. Thanks a lot.